This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. Okay, so on this lecture, we're going to introduce open sets, first on the real line, and then we'll move on to several real variables. So we say that A in R is open in R, and that'll become important later on when you're dealing with open and relative to other sets. If for any point in A there exists an epsilon greater than 0, such that x minus that epsilon and x plus that epsilon, that open interval is contained within A. So essentially what you're saying is for any point in the interval, we can take epsilon really, really small, and then in general, that's what you do. You can move a little bit to the left and a little bit to the right, a tiny little amount, and you're still going to be contained within A. So an example of that's not open is this closed interval from 0 to 1, because if we take the points 0 and 1, if we move even the tiniest bit left of 0, and no matter how small the epsilon is, we're going to get something that's outside of the interval. And the same for 1, if we take anything a little bit bigger than 1, we're going to be out of the interval. However, if we take this open interval here, 0 to 1, this is open, and that's why we call it an open interval. And if we were to take a point really close to 0, because we can't actually take 0 as our point, because again, 0 is not in this interval, right? This interval doesn't have a minimum, it only has an infimum. So we can't take x to be 0. We can take x to be really, really close to be 0. However, with the real numbers, you can always zoom in really close, and no matter how close we took x to be 0, we can always just move an epsilon left and epsilon right without actually touching that 0. So for example, if this was the x here, right? Then we could take, for example, x over 3, and we can move x over 3 left and x over 3 to the right, and we wouldn't actually hit 0, because x over 3 to the left is just 2x over 3, not 0. Because we couldn't actually take 0 to be one of the points to test. And for the same reasons as here, these intervals here, where they're sort of open on one end and closed on one end, they are not open, right? So I've been using intervals open and closed on one end in the sense that it's a round and square bracket. From now on, open and closed will mean open in this definition. So if we were to take on this end, on the closed end, with the closed bracket, we couldn't move left at all, and same on this one, we couldn't move right at all. So if there's a single point in the interval which you can't move a little bit left, a little bit right of, and stay in the interval, you are not working with an open set. Open sets have this behavior here. I put an exclamation mark because this is very important when you get onto topology. So every union of open sets is open. So it means, in a sense, you can take infinite unions of open sets and it'll stay open. However, only finite intersections of open sets are open. Here's an example to show this. If we take for every n, set an to be defined as the interval from -1 and 1 over n to 1 over n for all the natural numbers, this is open in Rn, right? You can test this. It's open for the same reasons that this is open. It's just an open interval. However, if we were to take an infinite intersection of these open sets, which we would define as so, just the intersection from n equals 1 to large n, just take a limit as n goes to infinity. Well, we can just look at the behavior of each of these ans as they go to infinity, and luckily it's symmetrical, so we can just look at one of the bounds, and you can see that very obviously as n goes to infinity, this just goes to 0, which means that this limit here will just converge to the point 0. And individual points are not open, because if you were on the point, you couldn't move a little bit left or a little bit right and stay on the point. Okay, now, so in d dimensions, we need to first define an open ball. And this is actually the generalization of the open interval. So if we just set d equal to 1, this is just the definition of an interval, or an open interval. So the open ball of radius 0 centered at a point P in Rd is given by either P sub RP or VPR. And it's just the points in RD that lie within R, the radius of P when we take the vector norm. So we just get this ball here. I'm using dashed line to represent the fact that this is open. This is the openness comes from the fact that this is strict inequality here. In fact, we can get onto closed balls where this becomes a non-strict inequality, and we'll use a non-dashed line to represent that. So uh, now we can define an open set in RD. So let's take A in RD, and we call that open in RD if for any point x in A, there exists an epsilon such that the ball centered on x of radius epsilon is contained within A. This is equivalent to the definition from before. Because if this was one-dimensional, well, the ball of centered on x of radius epsilon in one dimension is just an epsilon to the left and an epsilon to the right. So this ball would drop down to just an interval. So we can see some kind of abstract examples here of open and closed sets. So this set here with these kind of dashed lines in general will indicate that the boundary is not included. We'll define the boundary formally later, where you can imagine that the points on the boundary are not within the set. So here, we could take any point, similar to before, and take a little epsilon ball around it. Again, epsilon will usually be small. You can take it as small as you like. And you can basically make this ball as small as possible and it'll fit within the set. For a set like this with the filled in line, this means that we're going to say that the boundary is in it. So all these points on the outside, which define the edges of the shape, they are also contained within the set. So for example, if we were to take a point on that boundary, right, because here the boundary isn't included, so we couldn't take those points. Here we can take one of those points, and if we were to draw a little ball around it, you can see some of the ball would lie outside of the set. No matter how small we make this ball, it will always spill over. And here we can see a set sort of like those intervals that we had that were a closed bracket on one end and open bracket on the other end. It's kind of the equivalent here. So some boundary points are included, some aren't. Here we can see not open because we couldn't draw on those areas where there's a boundary included. We couldn't we couldn't draw a small enough ball to get this part over here inside of a set. This property holds for open and closed sets in all dimensions. And just for convention, we will consider that the null set is open. The idea behind that is that there is no point in the null set. So there's nothing to violate this condition, right? There's no points in here such that this is violated. So by default, it'll be open. So a concrete example now of an open set would be, well, of course, there's the open ball. They are kind of maybe obviously open sets because you can just take the ball itself to be the open ball within the open ball. But here, this is what's called the upper half plane. So it's just the points in R2 where the y is strictly positive. So if we could take any point in the upper half plane, that means that its second component, P2, is positive. There's this point P here. So we can just set epsilon to be equal to that P2. So then for any point in R2, which has its y component lying within an epsilon of that point P2, well, epsilon is just P2, so this is equivalent to saying that y is just positive. Therefore, y will lie in the upper half plane. That means this point here will lie in the upper half plane. And this is just the definition of the ball centered on P1, P2. So that means that any point in H2, because remember this was completely arbitrary, you can take any point and just set the ball radius epsilon equal to P2. That point will actually be contained within the upper half plane Just drawing it here, so it'll come all the way down, and because this y-axis isn't actually included in the upper half plane, this ball can be big enough to like graze the y-axis if you like. It's not actually included in it, and it'll be contained. If that feels a little iffy to you, you can just take the radius to be p2 divided by 2, and then it'll be even smaller, and then it'll be much more obviously still contained within the upper half plane. So now we're going to get onto a slightly similar issue, but the difference is subtle, but it's important. Basically, we have open balls in subsets of RD. So it's an open ball relative to that particular subset. So again, open ball in a subset A of RD of radius R tangent on P in A is given by, which is going to be denoted by this little subscript here of an A. It's all the points in A which are within our distance of P. So now we can get onto the idea of relatively open sets. So before I was clarifying something was open in RD. Now if we had y subset of x subset of RD, we can have that y is open in X if for all y's, all points y and y, there exists an epsilon such that the x ball centered on y of radius epsilon lies within y. So the x ball, like the a ball here, it's the open ball in F. So now, if we look at an example, we can look at why this is an important distinction. If we take S1, which is just the unit sphere, that's all the points xy, where x squared plus y squared equals 1 in R2, and we take x to be all those points which obey that, and y is positive, it's clearly a subset of S1. Because we can write x as just the intersection of h2 from before, the upper half plane, intersection with S1, right? That's just this definition here, intersection with this definition here. Because of that, x is open in S1. You can convince yourself of that definition. So for any set A that's open in RD, that set intersection with any set B will be open in B. However, this set X is not open in R2. So for example, if we were just to look in the R2 setting and were to take the point 0, 1 up here, and were to take a ball radius epsilon around it in R2, this is the R2 ball, right? We can see clearly it lies outside of the area of X. However, here it's just the X picture, right? So now the ball radius epsilon, the S2 ball radius epsilon, if epsilon was like small here, that looks almost like a curved interval on the top of the set X, and that does lie within X. So you can convince yourself with this definition here that the S2 ball, this would it would follow the natural geometry because you're only considering the points that already lie on S2. So that's how you can kind of encode the curvature in there, if you like. So that's why it's important to clarify. If we're talking about open in general, we'll just mean open in respect to RD, but we'll say open in another set if we want to clarify that it's this sort of relatively open with respect to a ball within that set. So two very useful exercises to try is to prove that for any subset X of RD, a point in it and positive radius, that the what we call the open ball in X is in fact open in X, and that this set here, where we reverse the inequality, is also open in X. So it's not quite the complement because you don't have the points where it's equal to the radius. Both of these are useful to do, this one especially when we get to closed sets. Here is now an alternative statement about convergence as it relates to open sets. So beforehand, we just wanted to have like a ball of radius epsilon that could shrink around the limit point after some potentially large natural number in the sequence, and after that, all of the members of the sequence would lie within that ball. We can actually be much more general about it and say if we have any open set X where P is contained and XP being the limit point, that after some potentially large n, all of the sequence members will lie, this should be regular n as well, should lie within that arbitrary open set, which might seem a little unintuitive to begin with, but they actually are completely equivalent statements, and it's a little easier to prove to yourself in R1. Now here we can talk about the properties of sets that are open in X. So if X is any subset of Euclidean space, then the collection of open subsets of X are as such. The null set and X itself are both open in X. This is a very important one. I said before that the null set is just considered by convention to be open in X because there's no points to sort of not be able to wiggle around as such. And then X is of course open in X because again it's at any point within X you'll be able to create by definition an open ball in X. Again, arbitrary unions of sets that are open in X stay open in X, so arbitrary meaning potentially infinite, but only finite intersections stay open for the same reasons as we saw in the sets in R1. So an example then is if we take this set here, so it's the points in R2 that lie within this ball of radius 3 and that the y is positive. That set's open in X because it was the intersection of the open ball centered at 0, 0 of radius 3 and the upper half plane, both of which we've already shown are open. This is just a picture of it here. And that falls because of this property here as a finite intersection. Now this is a very interesting result. It says that if we have y as a subset of x, which is a subset of Rd, then y is open in X if and only if there exists some other set, some third set Z in Rd, where Z is open in Rd and y is of the form Z intersection X. So this might seem obvious one way, right? If we have an open set in Rd and we intersect it with X, that'll give an open set in X. So we just take this open Z and then some not open, or not necessarily open X, to the intersection this Y here, that Y would be open in X, but the converse mightn't be obvious to you. So I'll give a sketch proof for that now. So just to prove the statement that essentially all of the open sets must have this form here of Z intersection X, we're going to start with just taking any open subset Y in X, and for all points in Y, P, there exists some radius, potentially small, greater than 0, such that the X ball, open X ball, lies within, all that radius lies within Y. And this is just true by definition of Y being open. Now, if we consider the same radii that we have for each point, but as just regular balls in Rd, and then take Z for the union of all those balls as P ranges over all the points in Y, well, each of these balls is open in Rd because they're open balls, and arbitrary unions of open sets are open. So that means that this infinite union is still open because it's a union of open sets and Z is open. So now for any given P. This open ball in RD is when intersected with X, well, that's going to be a subset of Y, because that's just going to give the X ball. Then for any point Z in Z, so in this big union here, it has to belong to at least one open ball in RD. Again, that's just kind of by construction. So that means that since every point belongs in here, we can just take all the points and go from here to this thing, which is that Z intersection with X is a subset of Y. And now to prove the reverse inclusion, for any point in Y, that point P is clearly within the RD ball centered on P, which, as we know, is a subset of Z. Therefore, since all those points are in here, which is a subset of Z, that means that all the points in Y are in Z, so Y is contained in Z. And since Y is also contained in X, Y is contained in their intersection. So we have that Y is contained in this object, and that object is contained in Y, so therefore the sets must be equal.